Hello everybody, this is our Evidence 1 video for the subjects of mass and energy and musical expression.
Hi, my name is Angel Eduardo Clemente Perez and I'm going to expose our team's project. The project that we are doing is the Cube project, in which is a bulb, a ball, a bucket with water, and just that. So the objective of this project is to see the waves that are generated when we throw the ball to the bucket. So here I have the ball, which is the object we're gonna use to generate water waves, and here we have the bucket of water. So when we throw the ball to the bucket, we're gonna create sound waves and we're gonna create movement waves. Both of these waves generates a movement in water, and it can be a constant speed until it stops. So we're throwing now the ball to the bucket, and when we throw it, we can probably see the waves, but they are there. The waves of sound and the waves of motion. Thank you. So with this project, we can barely see the water moving, but in reality, the water is moving at a constant speed with the waves that it makes with the move of the ball. We can see that all the sounds and the waves of sound and the waves of water that are made are a product of just a simple movement with the ball.
Firstly, we must connect our experiment to the sound. Sound, as we know it, is a form of energy that travels through a medium as waves. Similarly, the waves we surf in the water represent a form of mechanical wave, just like sound waves. Our plastic ball makes contact with the water surface, it initiates vibrations. This principle is at the heart of sound production. Just think of musical instruments where strings, membranes, or reeds vibrate to produce the beautiful sound we enjoy. This is a clear example of it. Waves are defined by their frequency and wavelength. The frequency of the waves in our experiment corresponds to how often they rise and fall. The wavelength, on the other hand, is the distance between successive wave peaks. These concepts directly correlate with the pitch and characteristics of sound waves. Higher frequency waves produce higher pitched sounds, while longer wavelengths are associated with deeper tones. Well, just as in music, our experiment involves harmonics. Harmonics are multiples of the fundamental frequency. While our primary focus is on the primary wave generated by the plastic ball, you can observe secondary waves or ripples, harmonics, shaping the overall pattern and sound of the waves.
Propagation speed. Just as sound waves travel through a medium at a specific speed, our experiments wave move through the water at their own characteristic speed. This speed can be calculated by dividing the wavelength by the period, an essential concept in understanding wave behavior. Period. Period refers to the time it takes for one complete cycle of a wave to pass a given point. Understanding the period is fundamental to understanding frequency, which, as we've discussed, is essential in both wave and sound analysis. Vibe. Vibe often describes the overall feeling of atmosphere. The observer's perception of the waves, characteristics, and variations contributes to the overall vibe of the experiment, much like how music can evoke different emotional vibes. Doorbell. A doorbell produces sound through vibrations similar to how the plastic ball creates vibrations in the water. While the direct connection to a doorbell is incidental, it reinforces the role of vibrations in sound production.
So we have the first one, tempo, that is not exactly related to our activity,
but we can draw like an analogy between the tempo of a musical composition and the rate at which we release the plastic ball. A slow release creates a tranquil rhythm, while a forceful one creates a mimic and a rapid crescendo. Agogic. Agogic refers to expressive timing or emphasis to music, finds in parallel in an experiment. Variations in a plastic ball release or impact generate expressive patterns in the waves, emphasizing certain aspects of their motion and reflecting the concept of agogic in music. The third one is material density, linear. This density of materials, such as water and plastic balls, for example, play a role in the wave behavior. Denser materials can influence how waves are generated, much like how material density affects the transmission of the sound. Musical figures. Are distinctive patterns or motifs in music. In our experiment, we can observe how the waves from specific shapes or figures as they propagate, drawing a loose analogy to musical figures in a composition. Melody, the last one. While our experiment doesn't create exactly a melody in the traditional musical sense, it allows us to explore how different methods or realizing the plastic ball resort in varying patterns of waves, akin to variations in a musical melody. And this is all.
Well, now to measure the speed of sound in a fluid, which in this case was water, we use this formula right here, which means the square root of the bulk modulus divided by the density